Welcome to this lecture on one of the most fascinating failures in classical fluid mechanics, the Risotto paradox. This is a story about how our understanding of suspensions completely broke down when confronted with a simple kitchen phenomenon. Let's begin with what classical fluid mechanics predicted. When you cook rice in water, you have solid grains suspended in a liquid. The classical theory made a very clear prediction. Rice grains in water should behave as a simple suspension. As the grains cook, starch molecules dissolve into the water uniformly. The viscosity of the suspension should increase smoothly and continuously as more starch dissolves. This is what Einstein's theory of suspensions predicts. Einstein gave us this famous equation for suspension viscosity. Eta equals eta 0 times the quantity 1 plus 2.55 plus higher order terms. Here eta is the suspension viscosity, eta 0 is the solvent viscosity, and phi is the volume fraction of particles. This equation assumes that particles are uniformly distributed and that viscosity increases continuously with concentration. It's a cornerstone of classical fluid mechanics. But when we actually look at risotto, something completely different happens. The behavior violates every prediction of classical theory. In risotto, the grains remain firm and separated. They don't dissolve uniformly. Yet the sauce between them becomes incredibly creamy and viscous. How is this possible? The sauce thickens dramatically, but the grains themselves remain intact. This contradicts the continuous thickening model completely. Classical diffusion theory would predict that starch should dissolve uniformly from the entire grain surface. But that's not what happens. So scientists decided to actually measure what was happening at the microscale. What they found was revolutionary. Measurements showed that only the outer layers of the rice grains release starch, and only under mechanical shear stress. This is not uniform diffusion at all. Here's what actually happens. The rice grain has a core that remains intact, but the outer layer forms a gel-like structure. When you stir the risotto, mechanical shear abrades this gel layer and releases starch granules. This completely violates the classical assumption of uniform diffusion. The starch release is not governed by Fick's law, it's governed by mechanical processes. This forced a fundamental realization. Risotto is not a simple suspension, it's a complex non-Newtonian system. Let me ask you a question. What is a non-Newtonian fluid? It's a fluid whose viscosity depends on the shear rate. Unlike water or oil, where viscosity is constant, non-Newtonian fluids can become thicker or thinner when you apply stress. Mathematically, we write eta equals eta of gamma dot. The viscosity eta is now a function of the shear rate gamma dot. Risotto exhibits what we call shear-thinning behavior. The harder you stir it, the more the outer gel layers abrade, releasing more starch and changing the viscosity in complex ways. Let's get quantitative. We need to understand the properties of this surface gel layer that classical theory missed entirely. The gel layer thickness delta is approximately 50 to 100 micrometers. This is incredibly thin compared to the grain size of several millimeters. If a rice grain has a radius of about 2 millimeters, this gel layer is only 2 to 5% of the total radius, yet it controls the entire rheological behavior. The storage modulus G' of this gel is approximately 10 to the 3 to 10 to the 4 pascals. This tells us the gel has significant elastic character. Compare this to water, which has essentially zero elastic modulus. The gel layer is neither a solid nor a simple liquid. It's a viscoelastic material. To describe the rheology of the risotto sauce, we need to abandon Newton's simple viscosity law and use a power law model. The shear stress tau equals K times the shear rate gamma dot raised to the power n. Here K is the consistency index, and n is the flow behavior index. For a Newtonian fluid like water, n equals 1. The stress is directly proportional to shear rate. But for risotto sauce, experiments show n is approximately 0.3 to 0.5. This is strongly shear-thinning behavior. The consistency index K is approximately 5 to 20 Pascal seconds to the power n. This is orders of magnitude larger than water's viscosity of about 1 millipascal second. Now let's talk about the mechanism that classical theory completely missed: mechanical abrasion. When rice grains collide during stirring, the gel layers rub against each other. This mechanical abrasion tears off starch granules and releases them into the sauce. The rate of abrasion depends on how often grains collide, which depends on the stirring intensity and grain concentration. The mass release rate m dot is proportional to n times versus times A, where n is the number of collisions per unit time, v is the relative velocity between grains, and A is the contact area. Classical fixed law diffusion would predict a constant release rate that depends only on temperature and concentration gradient. But abrasion is purely mechanical and depends on how you stir. Let's do some numerical estimates to see how much starch is actually released and why it has such a dramatic effect. A typical arboreal rice grain has a mass of approximately 20 milligrams. During risotto cooking, about 20% of the grain mass is released as starch. That's about 4 milligrams per grain. In a typical risotto recipe, you might use 300 grams of rice in about 1 liter of liquid. The total starch released is 300 grams times 0.2, which equals 60 grams. The starch concentration in the liquid is 60 grams divided by 1,000 milliliters, which is 6% by weight. A 6% starch solution has a viscosity hundreds of times higher than pure water. This is why the sauce becomes so creamy. But wait, there's more complexity. Not all starch is the same. Rice starch contains two types of molecules with very different properties. Amylose is a linear polymer of glucose units. It makes up about 20% of rice starch. It's relatively mobile in solution. Amylopectin is highly branched and makes up about 80%. Its branch structure makes it much more effective at thickening. The intrinsic viscosity, written as eta in brackets, equals eta minus eta 0 divided by eta 0 times C. This measures how effective a polymer is at increasing viscosity. For amylose, the intrinsic viscosity is approximately 100 milliliters per gram. But for amylopectin, it's 200 to 300 milliliters per gram. Amylopectin is much more effective at creating viscosity. This brings us to an interesting culinary question. Why is arboreal rice specifically used for risotto? The answer lies in the physics. Arboreal rice has a high amylopectin content, typically 70 to 80%. Some other rice varieties have less. Arboreal grains are also physically larger, with more surface area for the gel layer to form. Surface area equals 4 pi r squared. If arboreal grains have radius 2 millimeters versus 1.5 millimeters for regular rice, that's about 78% more surface area. More surface area means more gel layer and more starch release during mechanical abrasion. This is why arboreal creates a creamier risotto. Let's talk about temperature. Why must risotto be cooked at a specific temperature range? Again, the physics gives us the answer. Starch gelatinization occurs at approximately 65 to 70 degrees Celsius. Below this temperature, the starch granules don't absorb enough water, and the gel layer doesn't form properly. Below 65 degrees, you don't get proper gel layer formation. The grains stay too hard and don't release enough starch. Above 100 degrees at atmospheric pressure, the grains can overcook and disintegrate completely. Then you lose the paradoxical behavior and just get porridge. Diffusion follows an Arrhenius equation. D equals D0 times e to the negative EA over RT, where EA is the activation energy, R is the gas constant, and T is absolute temperature. But remember, in risotto, mechanical abrasion dominates over diffusion. Temperature affects the gel properties more than the diffusion rate. Here's something classical theory completely misses. The way you stir the risotto actually changes its physical properties. Let me explain why. If you stir gently, you get less abrasion and less starch release. The risotto will be less creamy. If you stir vigorously, you get more grain collisions, more abrasion, and a creamier texture. But if you stir too vigorously, you can break the grains completely and create a mushy texture. There's an optimal stirring intensity. The shear rate gamma dot is approximately versus over L, where V is the stirring velocity and L is a characteristic length scale. Experiments suggest that optimal risotto results from shear rates of about 10 to 50 per second. This is vigorous, but not violent stirring. Let's compare risotto with other starchy systems to understand what makes it unique. Regular boiled rice has no mechanical abrasion. Grains don't collide, Some starch leaches out by diffusion, but not much. Pasta releases starch by surface erosion and diffusion into the boiling water, but pasta is made from wheat, not rice, and has different starch properties. Oatmeal involves complete grain disintegration. The oats break down entirely, and you get a uniform suspension, closer to classical predictions. Only risotto maintains this paradoxical combination: intact grains that stay firm and separated, while simultaneously creating an extremely creamy, viscous sauce. Let me now explain precisely why classical fluid mechanics failed to predict risotto behavior. Classical theory assumes particles are rigid and inert. They don't change during flow. But rice grains develop this reactive gel layer that responds to shear. Classical theory assumes uniform properties throughout the suspension. But risotto has a dramatic gradient from the grain core to the gel layer to the sauce. Classical theory often assumes Stokes flow with negligible inertia. But grain collisions are inertial events with significant momentum transfer. The Reynolds number Re equals rho VL over mu. For grain collisions in risotto, Reynolds numbers can be 10 to 100, well outside the Stokes regime. The modern understanding treats risotto as a complex, multi-phase system with coupling between phases. Phase 1 is the intact grain cores. These are essentially solid particles with minimal interaction with the liquid. Phase 2 is the surface gel layers. These are viscoelastic, neither solid nor liquid, and respond dynamically to shear stress. Phase 3 is the dissolved starch in the continuous liquid phase. This is a non-Newtonian fluid with complex rheology. All three phases interact. Mass transfers from the gel layer to the solution. Mechanical forces couple all three phases together. Now let's talk about the broader implications. This isn't just about cooking. The physics of risotto has implications for many industrial processes. Pharmaceutical tablet coatings can form gel layers that abrade and release drugs in a controlled way, just like risotto starch. Mineral processing and ore grinding involve shear-induced abrasion of particles with surface layers of different properties. Bioreactors with cell aggregates can show analogous behavior where cells at the aggregate surface behave differently from the core. The risotto problem taught engineers and scientists that classical suspension theory is insufficient for many real systems. We need to consider surface layers, abrasion, and non-equilibrium effects. Let me give you a thought experiment to quantify exactly how paradoxical this behavior is. Imagine we took 60 grams of starch and dissolved it uniformly in 1 liter of water with no rice grains present. The viscosity would be approximately 50 to 100 millipascal seconds. This is about 50 to 100 times the viscosity of water. Now imagine adding intact cooked rice grains to this solution. Classical theory predicts the viscosity should increase further because of the particle volume fraction. Classical Einstein theory gives Eta classical equals Eta's solution times 1 plus 2.5 phi, where phi is the grain volume fraction. But experimentally, risotto viscosity is actually much higher than this prediction. The interaction between grains in the sauce creates additional thickening that classical theory cannot capture. The answer lies in the interactions between the gel layers and the starch solution. These interactions are highly nonlinear. We need terms like k-phi squared or even higher powers to capture the nonlinear interactions. This is far beyond classical linear theory. The gel layers continuously abrade and release more starch, dynamically adjusting the viscosity. It's a feedback system that classical theory cannot describe. Armed with this understanding, we can now answer questions that classical theory could not. Question: why does risotto require gradual addition of hot broth during cooking? Answer: because the gel layer formation and abrasion must proceed at the right rate. Adding all liquid at once would overcook the outside before the inside is ready. Question: why does standing time after cooking improve risotto texture? Answer: the gel layers relax, starch continues to hydrate, and the viscosity equilibrates. This is a viscoelastic relaxation process. Question: why does reheated risotto lose its creamy texture? Answer: the starch retrogrades during cooling, forming crystalline structures that reduce viscosity. Heating again cannot fully reverse this process. Let me describe the mathematical challenge of modeling risotto properly. This is an active area of research. We need coupled partial differential equations for momentum, mass, and energy transport, with moving boundaries and phase transitions. For starch concentration C, we have partial C, partial T, plus divergence of C times velocity versus equals divergence of D gradient C plus source term S. The source term S represents abrasion and is extremely difficult to model. The rheology is both shear rate dependent and time dependent. We need constitutive equations that capture shear thinning, thixotropy, and viscoelasticity simultaneously. There is no analytical solution to the full risotto problem. We must use computational fluid dynamics with advanced numerical methods. What is the larger lesson here for science? The risotto paradox teaches us something profound about the nature of scientific understanding. Even simple, everyday systems like cooking rice can completely violate our best theories when we look closely enough. The assumptions underlying classical theories must always be questioned. Einstein's suspension theory is beautiful and correct within its domain, but that domain is more limited than we thought. Mechanical processes and chemical processes can couple in unexpected ways. The mechanical abrasion controls the chemical dissolution in risotto. Multi-scale physics is essential. We must understand behavior from the molecular scale of amylopectin to the grain scale to the pot scale. Let me summarize this scientific revolution that started with a cooking problem. Classical fluid mechanics predicted that rice and water would show continuous, uniform thickening as starch dissolved by diffusion. Reality showed a paradox. Grains remain intact and firm while the sauce becomes intensely creamy. This should not be possible under classical theory. The mechanism turned out to be surface gel formation, shear thinning behavior, and mechanical abrasion driven by grain collisions. The system is strongly non-Newtonian, with flow behavior index N between 0.3 and 0.5. The resulting sauce has viscosity hundreds of times higher than water, created by just 6% starch concentration acting through nonlinear rheological mechanisms. This discovery forced a complete revision of how we think about suspensions with reactive surfaces and mechanical abrasion. I want to leave you with some final thoughts about what makes this story so scientifically important. Science advances most when our predictions fail. The risotto paradox was a gift because it showed us exactly where classical theory breaks down. Kitchen physics can reveal fundamental principles. You don't need a particle accelerator or a telescope. A pot of risotto contains profound physics. True understanding requires integration across scales and disciplines: molecular chemistry of starch, material science of gels, fluid mechanics of suspensions, and mechanical engineering of abrasion. Sometimes the simplest question, like why is risotto creamy, requires the deepest answer. This is the joy of physics.